All right, hello and welcome to this geometry lesson via video instead of in class and in person. I would like you, once everything is adjusted, sound, you got your headphones in, all ready to go, make sure that you open up your notes. We're going to be building off what we talked about yesterday. So yesterday we transitioned from studying inductive reasoning to getting into deductive reasoning. And part of deductive reasoning is understand conditional statements. So we have to understand how if-thens work. So what we worked on yesterday is we took some statements, okay, we wrote them as if-thens. And then we looked at how do we write their converse, remember this, converse, inverse, and contrapositive. Now our goal today is to see what it takes to write a good definition. In fact, I'm going to go back to, this is what we talked about yesterday, this example about Olympians are athletes. And I believe I asked you, would that be a good definition? If I was writing the dictionary, would it be a good definition to say Olympians, well, they're athletes? No, that wouldn't be a good definition. Why not? Even though the if-then statement, if they are an Olympian, then they're athlete is true, okay, it still wouldn't be a good definition because its converse was false. If they're an athlete, then they're an Olympian. Okay? So if that was my definition, anybody who is an athlete would be an Olympian, and that's not true. So today we're going to look at a couple geometric examples, perpendicular lines, parallel lines. We're going to see what it takes to write a good definition and how do we do it. All right, so write the definition of perpendicular line. So we have to recall, and I hope that most of you do, what this word perpendicular means. Okay? Now I hope you recall that being perpendicular means that two lines intersect to form a right angle. Now what I want to do is, instead of writing it like this, where we say perpendicular lines are two lines that intersect to form a right angle, we put it into an if-then form. Because we know that it's not just the statement that's important, we have to look at the converse as well. So the way that I would write that would be, if two lines are perpendicular, then they intersect to form a right angle. That's my if-then statement. Is that true? Yes, it is true. That's what it means. If I know two lines are perpendicular, I know they intersect to form a right angle. But that's not a good definition yet, because we have to consider the converse. So converse, show me your if and then. What do? Take the if then and switch it. Okay? So how would I do that? I would, let's see here, hold on. Don't write this down yet. I'm going to show you something that is just needs to be tweaked a little bit. If I literally take the first half of the sentence and the second half of the sentence and I switch it, I would write this. Okay, so again, don't write this down. Okay. Here's what I just said. If they intersect to form a right angle, then two lines are perpendicular. Okay. I was not a terrific English language arts student when it came to writing, but I recall my English teachers having a little bit of an issue starting off a sentence with something like they in it when we don't know what the they is yet. Okay. If they intersect, what is this they? We don't know yet. So what I should do, what I should say is, if, what is the they that I'm referring to? It's the two lines, isn't it? Okay. I want to say if two lines intersect to form a right angle, then, now what can I use here instead? They. If two lines intersect to form a right angle, then they are perpendicular. Okay. That would be the best way to write that converse. So that's good. Go ahead and take a second and write that down. All right, you like my pausing technique and take a drink of water, give you guys time to write? Yeah, I know, it's good. So, are both of those statements true? Is the original if-then true? Yes, it is. How about the converse? Yes, it is. So that's my big test. Okay. Are would the original if then and the converse both be true? If the answer to that is yes, we can write the definition as what we call a biconditional. Now, take a look at that word biconditional. It starts with bi, like bicycle, referring to two. The reason that we call it a biconditional is because it works two different ways. It works this way, like our original did, and it works this way, like the converse did. It works in both directions. It's a biconditional. Now, biconditionals contain a certain phrase that we have to put in there every time. Biconditionals include the words if and only if. So it's not an if-then statement. We get rid of the if and the then, but we put this phrase in there, if and only if. Have you ever heard someone say that before? You can go to the movies tonight if and only if you mow the lawn. Have you ever heard anything like that before? What does that phrase, if and only if, mean? Let's see if we can come up with it, and then we'll just break it down to make sure that we understand. Here's how I would write it. Two lines are perpendicular. What's the next set of words that are going to come? If and only if they intersect to form a right angle. Two lines are perpendicular if and only if they intersect to form a right angle. Good. Now, something that's just a helpful way to remember this, if we have this phrase, if and only if, okay, oftentimes in math, especially when you get higher up and you have a lot of things to write down, you use symbols for different words, for different phrases, things like that. Our symbol for if and only if looks like this. Okay, it's an arrow pointing in both directions to remind us that when it's an if and only if, it works this way, but it also works that way. That both the original if then, if two lines are perpendicular then they intersect to form a right angle, works, and so does the converse if we go the other way. If they intersect to form a right angle, then the lines are perpendicular. So it tells us that it works both ways. Okay? And that's how we write a good definition. If the original is true, if the converse is true, so we can write it as a biconditional, that's a good definition. Any questions? All right, well, let's look at our next example. All right, write the definition of parallel lines. So we have to recall, what does it mean for lines to be parallel? Okay, I'll give you a second. Say what it means in your head. You don't have, or out loud, I suppose. I'm not going to hear you anyway. What does it mean for lines to be parallel? If you said that they do not intersect, then you're on the right track. Okay? Parallel lines, I agree, are lines that don't intersect. But there's actually a little bit more to it. I want you to see if you can think of an example of two lines that don't intersect, but are lines that we would not consider to be parallel. They're out there. In fact, if you look around the classroom, I think you should be able to spot two lines that don't intersect, but lines that we would not consider to be parallel. Take a few seconds and look around and see if you can find examples of a pair of lines like that in our classroom. Did you spot any yet? How about this? Look at, let's see here, should I try this camera? Okay. So see this line in the corner of the classroom over here that's going vertically? That line right there, vertical line. Now compare that, okay, and take a look at that line, that horizontal line at the top of the back of the classroom, up there where the ceiling meets the wall. Okay. Do those two lines intersect? No, they don't. Would you consider them parallel though? I don't think so. Okay, let me use this as an example. Hey, when we picture parallel lines, we picture lines that look like what? They look like that. Or maybe they look like this. Maybe they're going that way. Okay, they could even be like this. That's fine. I'd consider those parallel. They don't intersect. But I would not consider these to be parallel. They're not intersecting, but I don't consider those to be parallel. Okay? So parallel requires one other aspect other than they don't intersect. So let's see if we can think about what is it that is true about lines that we do know are parallel. Okay? Look at lines in the ceiling. Okay? Look at the lines that are running this way. Are those lines parallel? Yes, they are. Okay? Look at the line down here on the bottom of the classroom where the wall meets the floor, and then look at the line up at the top of the classroom where the wall hits the ceiling. Are those two lines parallel? Yeah, they are. Okay? So what is it about those lines not intersecting, and they're still parallel though? They're not like this. Well, what we have here is parallel lines don't intersect, but they do have to be in the same plane. Okay, here's my plane. Okay. So if I have my lines like this, okay, not intersecting, are they in the same plane? Yeah, they are. Okay. What if the lines are like this? Would they be in the same plane? Could I hold that paper up and have both lines contained in that paper, in that plane? Yes, I could. But how about this? Can I hold that paper so the entirety of both lines are in that plane? No, I can't. Okay. So a key for us here, okay, would that be that they're coplanar and do not intersect? My if-then statement would say, if two lines are parallel, then they are coplanar and do not intersect. All right, that's true. Hey, so now we go to the converse. We want to write a good definition. That's not a good enough definition. Okay. What's the converse? Take the if and then and switch it. If, I don't want to say they, I want to say what the they is. If two lines, that's the they, if two lines are coplanar and do not intersect, then they are parallel. Are both of those statements true? Yep. So now we write it as a biconditional. The original is true, the converse is true. That biconditional, remember, has to include the phrase if and only if. So I would say, how would I say this? Two lines are parallel if and only if they are coplanar and do not intersect. So, a few minutes ago I said, you can go to the movies tonight if and only if you mow the lawn. What is that saying? If you mow the lawn, then you can go to the movies. If I saw you at the movies, that would mean what? You mowed the lawn. Biconditional, both directions. Very good. Now that we've covered these, what I think we should do is come back and write in what these words mean. We should write in good biconditional definitions for perpendicular lines and parallel lines, the ones that we just wrote. Okay? And then we'll describe what a biconditional statement is. Let's see if I can get a shortcut here. Let's see if this all works. Copy, paste. Nice. Oh, it did not work well. So that's our definition of parallel lines. We go back, get our definition of perpendicular lines. There. I don't know why that does that. Chops it up. That's good. And let's write in what a biconditional statement is. The statement can be written in both the original if-then and converse are true. Contains the words if and only if. Okay. If you'd like to pause the video while you write that in, you're welcome to do that. Let's draw in some pictures here too. Let's draw in something that looks perpendicular. So if it's perpendicular, what should I see? Well, that means there's a right angle there. So I should see that right angle symbol, that little box, that little square in the angle. And let me just do something else here with it. I'm going to name these lines. There it is. So let me call this A, B, C, and D. How do I say that they're perpendicular? What symbols do I use? I would say AB, so line AB, and then my perpendicular symbol looks like this. Okay, it's an upside down T, but it looks like two lines that are meeting, intersecting at a right angle. So I'd say line AB is perpendicular to line CD. Okay, that's how I would say that. Okay. Parallel lines would look something like this. Now I have a mark that I put on parallel lines so I know they're parallel, just like we have a mark for a right angle, is I put an extra set of arrows onto the lines. When I see that extra set of arrows, that's telling me that those lines are parallel. Okay, now let's talk about how do we write that symbolically. I've got line AB. I have line CD. My parallel symbol is that. Looks like two parallel lines. Vertical, going up and down, but two parallel lines is our symbol for parallel. All right, last thing we're going to look at two examples, just double check that we know our terms, we understand what they mean. Use the diagram to decide if each statement is true or false. Line AC is, there's one of our new symbols, perpendicular. Line AC is perpendicular to line BD. Okay. Are these two lines perpendicular? Yes. How do we know? We see that they intersect to form a right angle, and we know if two lines intersect to form a right angle, then they're perpendicular. That is true. Angle AED and angle BEC are a linear pair. Okay, need to remember what a linear pair is. Well, that was chapter 1. Flip back in your notes, please. Chapter 1, find what we wrote down as the definition of a linear pair. Yep, still waiting. Flip back, find it, please. All right, what did we say a linear pair is? Look at that definition. First off, you should be noticing something. We didn't write a very good definition, did we? In fact, look at the other definitions in chapter 1. Did we write good definitions? Right? Biconditionals, did they conclude the words if and only if? No, they didn't. Okay, that's because we didn't know what a good definition was. So what I want you to do is pause this video, take the next couple minutes, and rewrite every definition in chapter 1 as a biconditional. Okay, I'm kidding. You don't have to do that. Okay, but moving forward, we are going to be writing good biconditional definitions from here on out. So what is a linear pair again? Okay, if I were to write it as a biconditional, I would say what? Okay, two angles are a linear pair if and only if they are adjacent and their non-common sides are opposite rays. So take a look. Are these two angles adjacent? No, they're not. I know that biconditional I just said works both ways, so it cannot be a linear pair. This would be false. These two angles are not a linear pair. They are a different kind of pair of angles, though, that we've talked about. They're vertical angles, aren't they? All right, last one. Use the diagram to decide if each statement is true or false. Angle GLK and angle JLK are supplementary. What's that word supplementary mean? Go back, look at our definition from chapter 1. You're not going to see a very good definition, though, are you? Definition of supplementary angles, we probably should have said, is two angles are supplementary if and only if the sum of their measures is 180 degrees. So take a look at it. Is the sum of these two angle measures 180 degrees? Yeah, they are. We know that because they're a linear pair. We see that line being formed here. This is true. What I'm trying to show you guys right now is how important good definitions are and how do we use them. I know that you guys can recognize supplementary angles pretty quickly, but what I'm doing is I'm checking to go back and understand, do we get how the definition works and how we test it to see if it is good? Okay, last one. Line GJ is perpendicular to line HK. Are those two lines perpendicular? Well, we have to ask ourselves, okay, why? Okay. I know you're saying right now, no, they're not perpendicular. You're correct. That's false. They are not perpendicular. But how do you know they're not perpendicular? Be very careful. Do not say because they look like they're not perpendicular. We don't do that in here. We don't say things like, oh, because it looks like that. It's kind of what our conversation was in our last lesson when we talked about the importance of reasoning. Euclid wasn't okay going with and just saying, oh, because it looks like. He went through and rigorously proved it. Okay? We want to have a reason. How do we know that they're not perpendicular? Because I could give you this diagram. Are those two lines perpendicular? Okay. Why? If you said yes, you can't say just because they look like it. Okay. The answer is we don't know. I don't know if those are perpendicular. Why not? Because I don't see something that tells me they are. If I see this, I know they're perpendicular. If I don't see that, I don't know. I can't say that they are. So going back to this one, does it have the right angle symbol in there? No, it doesn't. Okay, we're going to have to say it's false. Okay, so just be careful there. Don't assume things are what they are just because they look like it. You have to look for symbols and other things that you would know. So that wraps up our conversation. We've spent the last couple days looking at if-then statements, converse, inverse, contrapositive. We now know how to write a good definition using a biconditional. We know how to test things up against definitions to see if it really is true or if it's false. So with that, I'm going to wrap up my lesson. Thanks for tuning in, and I'll catch you next time.